everyone, and welcome to another STEMnet Virtual Research Cafe. This is our 15th one. Proud to say that. I'm Frank Gomez, Executive Director of STEMnet. Behind the scenes, we have Monica Alacon, Admin Analyst for the consortia. Much thanks to her for putting the logistics together and for publicizing today's event. The goal of the cafe is to help foster research collaborations across the CSU and catalyze submission of joint proposals. It brings together CSU assistant professors to share their work in a relaxed setting for 10 minutes each, Reason 10.0. We hope you'll find opportunities for collaboration and or learn more about their research that may impact your own program. Feel free to contact any presenter in the chat box, of course, when they're not presenting. At the end of all three presentations, they'll come together to answer questions. I'll be monitoring the chat box to call the questions from the audience. So let's begin. Once again, we have three wonderful speakers from across the CSU, and they're going to be presenting just a snapshot of their work. Our first speaker is Alexandra Chakarov from the Department of Computer Science at San Jose State. Alex, the floor is yours.
Oh, am I going first? I thought Nadia was going first.
Oh, okay.
I can go first though, if
no, we'll keep it. I guess on my end it was kind of so. We have Nadia Korovina from Chico State, Organic Molecules for a Brighter Future.
Excellent, thank you, Frank. All right, I will start my sharing now, and I apologize, I'm kind of on my phone, but it should be working. And here we go. Can everybody see my screen?
Yep.
Yes. Yep. Okay, excellent. I'm on my phone, so it could be a little, I can't see you guys, but I can see my screen. I just want to make sure everything's good. All right, thanks so much, Frank, for letting me join this research cafe, and thanks for letting me kind of showcase what I've been working on. I've been at Chico State for about 2 years now, and my research is in the area of organic electronics, and I have a very corny title for my talk. It's Organic Molecules for a Brighter Future, and I think you'll see why this is corny in just a little bit. So I'm going to start by talking about the problem, and the problem is organic electronic waste. And this problem is enormous, and the magnitude of this problem is very enormous. So in 2021, for instance, the statistics on electronic waste are such that 57 megatons of electronic waste was dumped in that year. And if you kind of need to think about this in terms of kilograms, because I think we're all, like, as chemists and as scientists, we're probably more comfortable on grams or kilogram scale. So 57 megatons is 57 with 9 zeros following it in terms of kilograms. And if you're trying to compare this to kind of something that is a little bit more comprehensible, so for instance, like the size of a small human being, so maybe like I'm probably like 49 kilograms. So, because again, yeah, we think in pounds here, but if you're trying to kind of compare this to kilograms, so if a 57 kilogram person will probably be a little bit bigger than me, but probably smaller than an average human being. And if you can kind of compare this electronic waste to the size of humans, this is about 1 billion small humans worth of waste gets thrown out in 2021. This is an enormous problem, right? And one of the components of this electronic waste is cell phones, and cell phones comprise about 10% of electronic waste. This is all based on the 2021 statistics. And the reason why this is happening is because the economy that we're currently using, the economy that the electronic industry is currently using, is kind of like a one-way economy. I like to call it the downhill economy, and not in a good way. So essentially where all of this starts is it starts in fossils, right? It's either fossil fuels that get converted to plastics or to other components in the cell phone, or it starts in like metal fossils. But essentially it starts in the ground. We dig it up out of the ground, then we do manufacturing, we construct all these phones, and then when we're done, we just literally dispose them. It just goes to the waste site and it just dies. It just goes there to die for the most part. I mean, there's a little bit of recycling efforts that are going on. And of course, like a lot of this, you've probably seen these horror stories of this ending up in Africa, and there are children in Africa burning the plastic off so they can take out a little nugget of metal out of these devices. But either way, it's terrible, right? Ideally, what we want is something like this. a circular economy where we're using renewable feedstocks to construct our materials and our devices. We do the manufacturing out of, and ideally we do sustainable manufacturing. And then when we're done, we either completely recycle the device or we biodegrade the device, or some combination of the two. But essentially, we want to avoid the landfill. And we want to do this in a circular way. We want to kind of not generate waste as we go while we're making these devices. So the components of a cell phone, I'm going to focus on cell phones today, and it has lots of components. Right? One of the big ones is the batteries. That's not the one that I'm going to talk about, but there's essentially a lot of pieces that we kind of all work on. And of course, as scientists, we kind of just focus on one little piece and we go deep into it and try to figure out how to deal with that. But there's a lot of pieces and there's a lot of opportunities for a lot of scientists to kind of try to figure out how to make all of these components either recyclable or compostable or some combination of the two. And the component that I'm going to focus on is going to be the screen here, namely the display and the molecules that are in the display of these cell phones. So if you kind of take a cell phone and you start zooming into it, when you look at the screen of a cell phone, so most of us, I think at this point, own a device that has an organic light emitting diode screen. And if you zoom into your phone, you literally just take a zoom, take something to zoom into your phone with like a microscope or something, you'll see this pattern of OLEDs inside, these pattern of pixels. And the blue ones are really huge because they're actually not phosphorescent, they're fluorescent pixels, but I'm kind of not going to go into those details today. But essentially, if you zoom in, you're going to see that the screen is comprised of these pixels in an OLED screen. An OLED stands for organic light emitting diodes. And then if you keep zooming into each of the pixels, inside of each of the pixels, you see a bunch of different layers. You see electrodes and a bunch of organic layers on the inside. And then if you keep zooming into these layers, then each of the layers is comprised of organic molecules. And if you look at the molecule, then you could kind of start to see different functional groups in this molecule. So me as a chemist, that's what I like to do. I really like to kind of zoom in and look at the molecules and then try to solve the problem on a molecular level. And the way that an OLED device, an organic light emitting device, works is you typically have two electrodes. One of them is going to be transparent. That's the one that the light passes through, and electricity passes through the device, and it enters the sort of this organic sandwich. So everything on the inside here, everything inside is organic. Well, not everything actually. It's mostly organic with a little bit of a caveat. And inside of this kind of organic chunk of material, there are these emitter molecules that are dispersed in them. So an emitter, or I'm going to call it kind of interchangeably call them emitters or luminophores. They're all referring to these molecules that actually make the light. So when you turn on your screen on your cell phone, electricity starts to flow, and then the electrons kind of combine, the holes in the electrons combine in the organic layer, and they create an excited state. And then that excited state eventually ends up on the luminophore or the emitter, whatever you want to call it. And then that luminophore is the one that emits the light. And again, because this problem is huge, right? The electronic waste problem is enormous, and I can't solve it all. But me as a chemist, I could pick one little piece of this problem, and I could try to solve that problem through kind of molecular engineering of just one piece of this entire electronics puzzle. So the emitters that are currently in your phone, the one like literally if you have a Samsung Galaxy or an iPhone, the ones that are in your phone right now are these iridium-based organic molecules. So in these molecules, you have three variations of a bipyridine or a phenylpyridine units, and they're usually substituted with something in order to like tune the color to whatever pixel you need of either red or green or whatever. But sort of the big problem in these organic luminophores is the iridium. And typically I kind of ask the audience, why is the iridium there and what is the problem with the iridium? So in order to answer the question why it's there because of how the excited states are created in organic light emitting diodes. There are kind of two possibilities for the electrons to I feel like I don't really want to go into the quantum mechanics of this because this is supposed to be an overview, but essentially there are two different types of electronic states. There's a singlet state and a triplet state. And when you operate an OLED device, the excited states are created through electricity. So you're mostly populating these triplet states. And if you're trying to get 100% efficiency, luminescence efficiency out of your OLED device, then you need to be able to harvest the triplet excitons, and that is done through phosphorescence. And the iridium inside of these molecules is what enables phosphorescence to happen. But there's a problem with iridium. And that problem, actually, before I tell you about the problem, I'm just going to remind you that these iridium compounds are already in your phones right now. They're mainly started when Samsung started manufacturing OLED screens, and they were actually developed in my PhD advisor's laboratory. So this is Mark Thompson. He was my graduate advisor. He holds most of the patents that are for phosphorescent luminophores. But there's a problem here. So it kind of, we as a society have been working with this, and it sort of has been fine for now, but eventually this problem is going to start staring us in the face. And that problem is that iridium is very rare. And in the way that it is incorporated into these devices, because it's such a small component, it's not recyclable. And why is the iridium rare? Iridium is rare on our planet because it's actually not native to our planet. So most of the iridium that we have here on this Earth, pretty much all of the iridium that we have here, came in the form of asteroids. And of course, the biggest source of iridium is the asteroid that killed the dinosaurs. So there's, a little bit of irony here. But if we're trying to solve the electronic problem, and I'm trying to solve the electronic waste problem on the small section of the displays of the cell phones, we need to have luminophores that either avoid iridium or recycle iridium somehow. And again, recycling iridium in this case is nearly impossible just because of how small that quantity is. So instead, we want to avoid using iridium. And ideally, what we want is, because we want to avoid electronic waste, when we're done with the device, we want the OLED screen to either be recyclable or compostable. And we already said that recycling is not an option. So instead, ideally, we want these luminophores to be compostable, so that when we're done with our device, we just throw it in the compost bin and it all just kind of becomes nutrients for the planet. So how do we do this? How do we make compostable luminophores for OLEDs? And kind of some of the requirements for this is that they have to be organic, right? So if you think of compost, what is compost? It's a bunch of carbon, hydrogen, oxygen, and nitrogen. So these have to be the only atoms that go into comprising our organic light emitting diode luminophores. They also must be able to convert electricity into photons efficiently. So this is where that singlet triplet thing comes in. And I'm not going to go into details of that, but I'm just going to say that the way that we design completely organic molecules to do that triplet conversion into photons is by coupling a electron donor and electron acceptor perpendicularly to each other, so that in the excited state, the electron kind of hops over from one side to the other. So if you want to know more about this, shoot me an email and I'll be happy to give you a full presentation on this topic. So we know how to do that. We know how to make completely organic molecules that convert electrons into photons efficiently. So we got that. And then the last part, this is kind of what I want to work on. This is sort of my niche here, is that I want these molecules to be biodegradable. And the kind of hypothesis that I had when I was starting this research is that maybe if we make the molecules, these kind of perpendicular molecules out of biomass components, then maybe that will make them more biodegradable, right? So if we're kind of starting from bio-like molecules, then maybe the molecules that we make in the end, because they will still have these kind of biological motifs, maybe the bacteria will like them and eat them really nicely. So this is kind of what we've been doing, and it hasn't been a very straightforward journey because kind of my group is working on multiple projects. One of them is just making these organic molecules more efficient at luminescence, but this sort of a new project is what we're aiming for in terms of the circular economy. And the way that we're going to approach this, the way that we're going to make these luminophores, we're already making them. We still aren't sure if kind of that last synthetic step is going to work or not, but we've been making kind of the precursors toward them. And the goal here is to make the luminophores biodegradable, and to start from some kind of a biomass waste. And one of the very common biomass wastes in California is walnut husks. So we know that especially in Northern California, in Chico, where we are, there's a lot of walnut farming. And the husks of these walnuts, they're complete waste. Nobody needs them. Nobody wants them. You can't compost them. You can't.
Excuse me, Nadia, can you close up your talk? Thank you.
Oh, okay. All right, that's it. That's what we're doing. All right, thank you very much. Goodbye.
Thank you, Nadia, for an interesting presentation.
Yeah, sorry, I'm on my phone. Let me try how do I stop the share? There we go.
Our next speaker is Brian Katz from Cal State Long Beach. He's from the Department of Mathematics and Statistics.
Hello, everyone. I'm Brian Katz, or BK. Any pronouns are fine for me. And well, so my my challenge is to talk a little about myself, the questions I find interesting, the methods I use, and potential research connections. So my last name is Katz. I do in fact love cats. These are my cats, Simon and River. They're named after a pair of siblings from one of my favorite TV shows before I knew that the show creator was a jerk. But I do very much love cats, and there are some cats in this presentation. My undergrad degrees are in math, chemistry, and music. Chemistry was not entirely by my choice, but I still enjoyed it. I mostly use it for baking. But I spent most of my energy on math and music, and I'm still deciding if I want to be a choral conductor or a math educator. And for now, I'm just doing both. Not conducting, but I'm still singing a lot. Okay, so some critical experiences that got me where I am. This title is called Question Everything. So I grew up in the South as a queer, kind of Jewish kid, and that had several impacts on the way that I experienced the world. That I sort of was separated from a white Christian majority, at least in terms of how I was supposed to view the world. And as a queer kid in a place where that wasn't really something we were talking about a whole lot, it was a little like I could see the matrix code that operated social interactions, especially like toxic masculinity kinds of stuff. And but it was sort of impacting others, but it didn't it didn't have its hooks in me in the same kind of way. And so from both of these, I was sort of able to see systems that were powering society, but in a way sort of like partially from the inside and partially from the outside. And I think that was really formative for me. And then my sophomore year of high school, I had a lovely teacher who had a heart attack. It was fine over Thanksgiving, and he retired, but he retired immediately. And they replaced him with a local engineering graduate student who, in the parlance of the region, bless his heart, he tried, which means the opposite of that. But what it really means is like he obviously knew pre-calculus. And since I mentioned the matrix, we appreciated that he looked like Keanu Reeves, but he didn't know how to teach children about trigonometry. And so he would try, and then we'd say, let us talk to each other and figure this out. And then we'd come back to him at the end of class and say, we think this is what's going on. I think this is what we were talking about. And he'd give us some feedback, and he'd sort of point out things that he missed and do that. And then we believed that he used our lesson plans for the rest of the day. And what I got from this experience is that it was clear to me that I did not need a member of the mathematical priesthood in order to participate in mathematics, that mathematics was something that I constructed and that I could construct for myself, rather than something that was absolute and existed without me and had to be transmitted to me. And so some themes from those two stories, I think a lot about comparative epistemology, how different disciplinary worldviews think about knowledge and the construction of their discipline. And I also like to step outside of that discipline or that set of knowledge and look at it as a thing. So I went to grad school and I did my dissertation in what's called tropical algebraic geometry. This is an approximate picture of my dissertation. There existed an interesting mathematical object in sort of classical geometry, and then another object that was paired with it, and this function between them captured most of the information. So Think of it as like every possible way that this cat can play with his ball. And then there was this tropical world, which is sort of like a line drawing version of the classical world. So there's these maps that go from the classical to the tropical world, but a lot of the same structure was preserved. And so I sort of constructed this object here, which in this case is drawn by the Twitter account Poorly Drawn Cats. And then I, after finishing my dissertation when I was in a more teaching focused small liberal arts college position, I transitioned to doing math education research. And so some questions related to the themes of interest and that sort of like comparative worldview kind of stances are: how do students develop a disciplinary epistemology? What kind of variety in those worldviews do we see in students and experts, and in what ways are they different, and is that meaningful? And what are the implications for action from those different epistemologies? In particular, I believe that teachers who can only view mathematics as universal truth will make choices that center that universality in ways that continue to make math classroom a dehumanizing space. If math exists independent of humans, and that's what you believe about your discipline, I think you're going to make choices that say, I have to transmit this at children, or I have to imprint it on them. And I think those are problematic ways of going about math classrooms. And so how do I get some data related to these kinds of questions? This is some data from a project that I did several years ago. It's concept maps before and after a course that was about sort of, I mean, it was about triangles, but it was also about mathematical truth. And so I asked the students to make these concept maps, and this is the pair of maps from the same student. On the first day, she says, mathematical truth introduces undefined terms, definitions, and examples, which provide intuitions, decidability, and logic, which is needed for construction, and it's needed to test, which articulates contradiction. It's also needed for evaluation, which shows consistency, which creates the words that I can't see, deduction, and the consistency also produces theorems, corollaries, lemmas, and axioms. So in terms of the themes from before, a couple of things that pop out. Mathematical truth is the beginning of this tree. Everything flows from mathematical truth. And then I have asked a large number of mathematicians, well, not that many, but I've asked some mathematicians to look at these maps, and overwhelmingly they look at these arrows and say, I don't even know what that connection is supposed to be saying on the pre-course maps. The other thing that pops out for the mathematicians is that these three sisters at the end of the tree are problematic because theorems, corollaries, and lemmas are all results that we prove, and axioms are our assumptions. And for those to be framed as equivalent to each other is very worrying from a professor's perspective. From a student perspective, it makes perfect sense. These are the like sentences that are often in the box of the textbook that you can use all you want. They're equivalent. Doesn't matter where they came from that perspective, but that's not how I want my students to view truth. Many of my students also put, in place of axioms in this kind of position, they put definitions, which is even worse because a definition isn't even true or false. It's a convention, a connection between ideas. And then this is the same student's post-course map. She says, mathematical truth. First, we have ideas. From these, we assume, yay, definitions, intuitions, and axioms. So that moved positions. And through mathematical rigor, logic, and persistence, we can use constructions and examples to make conjectures that we can, then we can apply a type of evaluation where we use deduction, contradiction, and decidability, only to find out that we still have undefined terms. She's framing undefined terms as like ambiguity that we haven't fixed yet. That's not how the mathematicians we were reading about would have used it. Would have used it as like a term that I'm careful about, and hence not, I'm not using my intuition. So it's actually supposed to be a positive, but she's framing it as negative. So I worked on that afterwards. But so we test yet again and look for consistency in our results. And if that is true, we have theorems, corollaries, and lemmas, the ones that should be sisters. And then we have proof that there's such a thing as mathematical truth. Yay. Looking at all the maps, this one is much more circular. It aligns with expert perspectives. Some of them were psychological, how you come to learn a new fact. Some of them were maybe process-wise, how you produce a new mathematical truth, and others were more epistemological, where the nature of the mathematical truth comes from, which was my intention. But we got much more expert-aligned maps, which was exciting. And so stepping back, I mostly use qualitative methods that come out of sociology and anthropology to do this work, but, oh, and rhetoric, if you're interested, we can talk about that during the Q&A. And what kind of connections do I think would be productive? I have a colleague, Moyang Lee, who is in literature and studies representations of mathematics. And we've been having some conversations about mathematics as dreaming, which I think is really cool. Obviously, comparative epistemology, other teacher education, and other secondary, maybe elementary teachers, historians of science, other sociologists and anthropologists, or maybe anyone else here. And that's my email address. Thank you.
Great, very, very interesting talk, Brian. I'm gonna email you about some maybe some other opportunities in what we do here at STEMnet. Our last but not least speaker, and I'm reintroducing her, is Alexandra Chakarov from San Jose State in computer science and science education.
Well, good morning, everybody. It's still morning for another 30 minutes. This time change has really gotten to me. It is now very dark when I wake up. Can you guys all see this in presenter mode right now? Oh, so I, of course, that'll be good. So I'm going to talk to you guys about interdisciplinary computer science activities today. And first, I'll give you a little bit about me. I've slowly been moving west throughout my education career. So I started off at Wellesley College in Boston, did my PhD at University of Colorado in Boulder, and now I'm here as an assistant professor of computer science and science ed at San Jose State. And I've been here for about 9 months now, so I'm still very early on in my career. And as an interesting thing about me, I think we all miss travel a little bit in the time of COVID. And so I just wanted to share sort of a little bit of my travel adventures in the summer of 2019, back when the world was still normal. So I, myself, my husband, and two of our good friends took a trip to Paris to see the Women's World Cup. I highly recommend the Women's World Cup as an athletic event. The fans are by far the nicest fans I have ever met at any sporting event. And we just had a lot of fun, and we got to visit Paris and Budapest and Vienna. So those are just some pictures of that. And I really look forward to getting back to traveling again. What we're supposed to talk about today is I'm going to give you a brief overview of some of my work. And I sort of have 3 threads of research that I'm working on in the moment. I'm sorry, just a sec. The chat is in the middle of my slides, so I'm going to move that. So broadly, my work encompasses computer science education anywhere from kindergarten all the way through undergrad. And it has similar goals throughout the whole process. And the idea is really to increase access and retention in computer science, especially around students who have traditionally been underrepresented. And I have developed a variety of strategies for doing that. A lot of which focuses on creating activities that are interesting and relevant to a wide range of learners. And that's one of the reasons that my work tends to be very interdisciplinary, is that computer science is very applicable to all kinds of disciplines, but a lot of the activities, still revolve around learning to sort an array of numbers, which is, not the most interesting thing to anyone. And so my 3 threads of research, the first involves integrating computing into K-12 science classes, and this was the focus of my dissertation. And so the work I did here was to realize, one, that computing is becoming an integral part of the scientific practice, as you guys all know, and the fact that the new set of science standards came out back in 2013 now, but that was around when I was starting some of my dissertation work. And those standards really emphasize students doing science by having science classes employ the tools and skills used by professional science. So it was sort of a ripe space to work towards integrating computing. And one of the things that we noticed is that a lot of the work that had been done previously really focused on using simulations to drive that integration. And one of our observations is that the simulations, while interesting, still sort of keep students at the computer all the time. which is not, the most interesting to all groups. And so I did some work, preliminary work with Girls Who Code in the summer of 2016, where we actually explored physical computing. So think using sensors and little programmable microcontrollers or mini computers to collect real world data. And one of my observations is that students who had been sort of previously unengaged through that, like just in front of the computer piece of it, really perked up when they got to physically see something, kind of make that connection between what they were doing on the computer and the world around them. And so that led us to come back and pursue how we could actually integrate computing into science class using programmable sensors to collect this real world data to help answer, different scientific questions students had. So for an example, we had the students place sensors all over the school to monitor temperature and humidity, and sort of they were investigating if there was mold growing in their schools. You can imagine this made us very popular with the custodial services. But a really cool thing actually happened in that they found an area that had some mold growing in it. The students wrote a letter to the the facilities people with a mitigation plan, and then they offered to even continue using the sensors to monitor the environment to make sure that if the conditions sort of reemerged, that they would be on the lookout for it and could catch the problem before it happened. And so I think one of the things we noticed there is the students, not only was science now in their hands, but science also had gone beyond the classroom and into these real world experiences that were affecting them. And so that's been a big push of my sort of work in the K-12 space. But as you can imagine, COVID has sort of put a little bit of a hold on that, since it's been a lot harder to get into and actually be working in schools now. And as I've transitioned here to my role at SJSU, one of the things that I've been working on is actually working with teachers around developing computer science authorization. And so this is to address a need that, is in California and the United States as a whole, is for trained computer science teachers. And since we're not going to be producing a bunch of 22-year-old trained computer science teachers anytime soon, often what we've been doing is looking to current math and science teachers to be sort of our basis. And so one of the things that I'm working on right now is actually creating a year-long curriculum that'll be for a cohort of they can be any teachers, but often our recruitment comes from math and science. And we're really, a challenge we face is that, these are experienced teachers in their content area. And so we really want to, when we're going through the process, we don't want them to be learning to sort a list of numbers, right? We want to figure out how to ground the computer science content and problems that are interesting to them and tied to their discipline. So for example, things that we've been looking at are, exploring existing data sets, designing, automated experiments, and sort of seeing how computer science is relevant to the discipline that they're teaching. And then sort of in that same vein, we are designing here at San Jose State a new introductory computer science course sequence with funding from the Center for Inclusive Computing, with the goal of increasing the participation of women and underrepresented groups in our major, because we have a retention problem, as may be familiar to you, and that students will often come and take one class and then they decide that computer science is not for them, for a variety of reasons. But one of the main reasons often is that they don't feel that it's relevant, to their interests, and they don't see themselves as being a computer scientist. And so the idea is we don't want to ground our homework problems in sort of these abstract concepts that students don't necessarily see the application of until they get to an advanced course. We want to ground these introductory concepts in a variety of relevant topics that are accessible to a broad range of interests. And so we've done some work with this already in integrating computer science and biology through bioinformatics. But I think we really need to broaden our scope. So what I am looking for is experts in other fields to partner with to design and field test some of these activities. And so I am not an expert in chemistry or biology or sociology or math. And so it's hard for me to come up with things that are actually realistic. Like, it's one thing for me to write a paragraph sort of putting context around a programming assignment, but ideally I would really like these assignments to address problems that are relevant in these disciplines, so students can actually see why computer science is important. And thank you.
Great, thank you, Alex, for the great presentation. And now we open it up for questions from our audience. And I see David Hassenzal has a question. Yes, David.
Yeah, hi all. Thanks for some really awesome presentations. I really enjoyed it. I'm actually going to ask a question that'll go to Brian and Alex, because I can run down one floor almost any day of the week and ask Nadia questions. So don't need to do that. So Brian, I'm the Dean of the College of Natural Sciences at CSU Chico, which includes the Department of Mathematics. Our college is the single biggest hurdle to student success in the university, which is also true of most colleges of natural science that have math departments. It's long been my sense that we're hiring people with PhDs in mathematics to teach people who are underserved in high school in algebra. And it's not clear to me that those people are well equipped to teach the students that come to us, yet it's what we consistently do. So this also is to Alex, because I think there's a really good interface between your two proposals of using applied issues to teach computer science. And I think Brian's models would apply to computer science as well as math. So Brian, who should we be hiring to teach mathematics at the CSU to deal with this problem that we are preventing a lot of students from being successful at the end of their first year? So solve that problem for us, please.
Okay, so I'll just fix higher education or STEM education. Well, some good news first. I think that compared to when I did my dissertation, which, you know, like I left grad school in 2009, so it's been a little while. Current grads are much better versed in thinking about teaching and learning, and to some extent education research, and math PhD programs are taking their responsibility much more seriously to prepare graduate students to do that work. So there is some hope there. I think in your hiring and reviewing process, you can search committees don't often know how to read the teaching and learning statements, and so the people with more teaching experience often, like if we are empowered, we can help guide that conversation. But if we're not, so that could be a thing that at dean level you could build. And I would suggest any evidence of focusing on student thinking rather than teacher performance as a big indicator. And then I mean, it's a really subtle question, and there's all kinds of stuff about professional learning and mathematical knowledge for teaching and other kinds of things. But if you run a classroom where you get young people's thinking to be said out loud, the rest of it will spiral from that. You'll say, like, why did they think that thing? What other tasks might cause this? How do I sequence this conversation? How do I facilitate a protective discussion? What's important about the groups to make sure that this happens? Like, that stuff all flows from listening to young people's thinking. So that's not the answer I think you were pointing towards, but I think slight changes in hiring and professional development that focuses on listening to students' thinking is where I would go.
Thank you.
Oh, and send them to Project Next, which is a professional development experience for new PhDs in math specifically who are teaching math classes. It's so send them to us.
Mm-hmm. Yeah, I mean, I think professional development is a huge thing. And I think another thing is not equating having like the full spread of grades means that the class was rigorous. So I think like which I think sometimes, like, you know, when you had a traditional undergrad experience a while ago, that can kind of feel what it's supposed to be like, but it doesn't have to be that way, and having the expectation that it doesn't have to be that way too.
And then building on what Alex put in the chat, you may not be surprised based on what I said earlier today, but every class with me is a class in epistemology. Like, I don't, like, yeah, we're going to learn some calculus or whatever, and we're probably going to learn more calculus than we would have learned if I just tried to tell you the power rule. But the focus is going to be on what things do we know and how do we know them. And so, yeah, maybe the class starts a little slowly, but by the end, we're doing things that that would have, you know, overwhelmed them if they tried to memorize that, instead are like, obviously I can justify that. That makes sense. It fits inside this framework that I already understand, and I know how to apply it in the future. So I agree with Alex's point in the chat that focusing the lower division classes, not doing the soft racism of low expectations and making them computational, make them more about justification is critical.
Yes, I think my students hate me, but I think every question they have to tell me why. Like, you can tell me the answer, but like, why? And by the end of the semester, they're like, oh, like now we actually like remember these things instead of just like cram them for the test. So that's always a nice thing to hear.
If I can put my 2 cents in here, because I kind of hear these issues from many of the campuses at all levels, may it be from faculty, you know, all the way to the presidential level. My feeling is we need to find a better strategy mechanism on how we hire faculty here in the CSU. You know, the old paradigm of, you know, they don't fit our department or our campus culture, or do we need to really hire clones of those who are representative of many departments in the CSU? The metrics, the rubric on how we hire is very outdated. It's from a different century, if you ask me, and it has not evolved. You know, I say educational systems are like, they're like snails on Ambien in terms of how slow they move, okay? And I think Brian's comments, yes, they're important. They're not new in terms of, you know, there's always the question as to how do we fix our campuses, and are we really providing our students with real world tools and this toolbox for them to be successful. And last thing, the issue of professional development, that comes out a lot too in faculty and administrators I deal with. It's almost like, how do we fix it? Just throw professional development at it and it's going to fix it. That is not the cure-all, save-all. It could be an aspect of that in proposals and what campuses provide, but it's not that save-all from the heavens that's going to help an institution change a lot of the systemic issues within not only our institution, but because I think our institution is a bit more open in terms of issues of social justice and, you know, et cetera. I wouldn't want to be teaching in some other institutions and in other places in other states than the CSU. So I'm not trying to knock the CSU, because I think if it can't happen in the CSU, it probably won't happen anywhere else, if you ask me. More questions from our audience here. I do have a question.
I have one
Sorry.
for Nadia.
Sure.
So one of the sort of generic concerns about more biodegradable products, it's that they're less durable or things like that. Like how are the products, I don't know if they're developed enough for them to be prototypes, but how are the products turning out from your lab?
Oh, that's a great question. I mean, my products are not turning out for my lab yet. So that's a short answer. Long answer is that, so the way that, so for instance, like you buy yogurt, right? And it comes with this biodegradable spoon. If you keep the spoon like dry on your counter, even if you wash it like every once in a while, it won't biodegrade. It will only biodegrade in the presence of specific bacteria. And because the way that electronics are constructed, phones in particular, everything is sealed. So like most iPhones are waterproof, most Samsung Galaxies are waterproof. So there's no access for bacteria to get in there. So even if the compound itself is like biodegradable, it won't degrade until you like open it up and let bacteria into it. So that, yeah, that's an excellent question.
Thanks.
I have a question regarding high school computer science teachers. Can we say, and I guess this goes true with mathematics also, would you find that a high majority of them are up to date on their content knowledge?
Of computer science? Definitely not, because most of the computer science teachers like that exist in high schools right now are not like CS content experts. They are, you know, math and science and other teachers that have sort of like, I don't want to say been repurposed because they like have training, but I mean, it's very hard to attract someone who has, say, an undergraduate degree in computer science to the teaching field, given the other opportunities available to them. So I think one of the things that we have been exploring is like, it's more than content knowledge. So really exploring how we can take some of the pedagogical content knowledge that they have from their subjects and see how it can be applicable to computer science. Because I think the idea that we're magically going to get a bunch of expert CS content people running around is not going to be there. But I don't think that you necessarily have to be a content expert to facilitate a really good computer science class. So that's kind of where the strategies that we've been working on.
Can I ask a follow-up about that, Alex?
Yeah.
So there's like pedagogical content knowledge in teaching technology and teaching with technology.
Oh yeah, you could talk about PPAC too,
right.
Technological pedagogical content.
Exactly. And I'm a mathematician and I definitely use a lot of technology. And I and almost everyone I know learned the technology we know about. Somebody gave us like a vaguely working piece of code and said, Google it and figure out how you want to change it. And I can do that with my students, but it seems like because they're used to much more smooth interfaces than I grew up with, they often shut down. So can you tell us a little about because that seems like the challenge in your project, right? Getting non-computer science trained people to think about teaching technology. So I'm curious about that pedagogical content knowledge.
Yeah, so like one of the things we've actually been focusing a lot on is debugging. So how students handle problems. And how this brings itself about is if the teacher doesn't necessarily have sort of the content knowledge, like they aren't necessarily able to spot the problem right away. And so how they support the students to productively struggle, even if they don't necessarily see what's wrong. And so we've kind of been exploring the different strategies that they can use, from other classes around questioning or, the use of resources, such as becoming a smarter Googler, right? So your search term is more specific. And kind of seeing how they uptake that. And I mean, we're doing some like qualitative, like in the wild video analysis of that right now to see if we can see patterns that emerge. But yeah, it's challenging. And I think the hard part is that a lot of the like authorizations out there, like their goal is to just provide the content. It's like, oh, if you have taken like like a couple CS classes, then you will now magically be able to teach high school computer science. And you know, as sort of we all know, right, that's not how it works. Like, and if anything, that's also, you know, the problem that we see in the introductory college level, where we have, you know, PhDs who, you know, don't necessarily know how to teach an intro class. And so I think we've been really trying to swing it back the other way and be like, how can we really integrate this content into problems that are relevant to them and that can also build on the skills that they already have developed, like pedagogical skills that they've developed.
I like your comment in the chat box there,
Yeah.
Brian. So, yes, Brian.
Oh, I don't know if I have a cursed proof I could share with everyone if we've run out of questions to give you something to think about.
Sure, go ahead.
Okay, so here's a proof that's adapted from some work by Keith Weber and Laura Alcock. 7 is prime. If 7 is prime, then 107 is prime. Therefore, 107 is prime. It's a syllogism that's sort of like Socrates is a human, humans are mortal, therefore Socrates is mortal. And so it's structured in the way we think implications should work. And it turns out that all three of the sentences are true. If 7 is prime, then 107 is prime. Think of that one like a promise. If we have class on Saturday, then I'm going to bring cookies. My honor is preserved if we never have, because I brought cookies every day to class. Doesn't matter what day we had class. So all three of those sentences are true and they fit together in a syllogism, but it's horrifying as a proof. Yes, 7 is prime. If 7 is prime, then 107 is prime. Therefore, 107 is prime. Doesn't feel like it proves anything. And for me, that shows that we're not checking the truth of things in mathematics. We're doing something else rhetorical. And we use a tool called Toolman analysis about the implicit justifications going on in the background. And it's really cool to me that we can like pull this thing in from a different discipline. It names our disciplinary work, and then it allows us to teach that disciplinary work more explicitly because we finally have vocabulary for it. So I don't know if other people have similar connections, especially interdisciplinary connections. I'd love to hear about them.
Well, I think what I'm going to do is reach out to you, Brian and Alex. We write a lot of proposals, and it'd be interesting to see how we can apply some of your own expertise in some of the lower division courses, which I think you're most interested in going forward. We've written a couple IUSs, in fact, one with San Jose State that was funded on AI for the social good. Which is kind of up your alleys. I think we can, and we also wrote another IUS with math, with Stanislaus and Humboldt that has a social justice bent on it. So it'd be interesting to see what we can brainstorm and see what we could move forward on. So I'll reach out to the two of you going forward. So a little bit of time left. I'd like to thank all of our speakers for presenting. Very, very interesting, nice discussion after. Don't hesitate to reach out to any of them for future collaboration or future proposal. We have a few upcoming events. April 8th, 10 a.m. We have the NSF Robert Noyce Teacher Scholarship Program and CSU grantees. Our next virtual cafe is April 13th. That's a Wednesday. We have the cafes every month. I hope you'll be able to attend that. Thanks for attending today. Hopefully we'll see you at a future STEMnet event. Take care, enjoy the rest of your week, and be safe, and enjoy, at least down here in SoCal, the very, very nice weather. Take care, all of you. Bye.
Thanks for organizing. Thanks, presenters. Bye.